In the next chapter, we briefly consider systems. The understanding of the concept of a system is important because every model is the representation of a system. It was also shown in the example of the US finance system at the beginning of the last chapter 3. The most abstract definition of a system is a set of parts which interact by means of a set of links that connects the parts of a system. As shown in the illustration, a system can be represented as a graph, where the parts are represented as nodes, the circles, and the links, respectively the interactions, they are represented as lines or arrows showing the direction of an interaction. The links can represent any kind of interaction between two nodes. These elements are the basis for every computational analysis or simulation of a city or region, independent of the complexity of the resulting model. So all kinds of models can basically be represented by nodes and links, by elements and the behavior or the interaction between these elements. Similar to the process of creating a model, the definition of a system depends on the elements we want to include or represent. In addition, we explicitly look at the system boundary here. This is important to be aware that every system has a boundary. It means everything we consider in a scientific context for a detailed investigation is separated from its environment and context. So if you want to study a certain phenomena in natural sciences, usually you take it from its environment, cut something out and carry it in a lab, and then analyze it, separate it from its context, separate it from its environment, that you can understand the behavior of the system or the element that you analyze. Therefore, the entities inside the system are all those necessary for it to fulfill its purpose. So you should not forget some important elements that you should include in the system, otherwise you cannot fulfill the purpose for which you have made the model or the system. The entities in the environment are all those things that affect the system but cannot be controlled by the system itself. That's the second important aspect if we consider systems. And finally, anything not in the system and not in the environment has no effect on the system's behavior. Only in the real world, everything is connected to everything else. So from our model and systems perspective, the reality may be considered as the most complex simulation that we can imagine. With a nice illustration of the system of a cow, we can see that there are inputs and outputs to and from a system. This means that there is a controlled information flow between the system and its environment. Later in our models, these input parameters, for example, are the control parameters, and the result of a simulation can be considered as the output of a system. But of course we can also link output and or the output of one system to the input of another system. This means that we connect individual systems with each others. So the result of a simulation or analysis can be linked to another system, another model, as its input. This allows to couple various systems and to create a system of subsystems, as it is shown in this very simple diagram on the slide. A very important differentiation between various systems is the way how they are modeled. On the one hand side, there are equilibrium models that converge to an equilibrium level in which the output of the model does not change anymore. On the other hand side, there are non-equilibrium models that at most arrive at an equilibrium level temporarily, but usually change its output continuously. Equilibrium models we can find often in economics, where the models are very abstract, as you've seen in this finance system in the beginning, and where the model system represents only very specific aspects of the reality without a lot of interactions with the environment. Non-equilibrium models in turn, they are usually used, for example, in ecology, where we try to understand the rules of the continuous changes of relatively complex natural systems, like the development of an animal population in a certain region, where the animals interact with each other and with their environment, and some populations may grow, others decline, and there may be some oscillating changes of these populations. But there will be never an equilibrium state where all populations stay at the same size, for example. So it's always changing and modulating. Non-equilibrium models therefore try to come closer to reality, but they are much harder to control or to analyze and understand than equilibrium models are. Because you can only try to understand some rules or some key mechanisms in the model, but you don't get one output value that you can consider it as the final result of the model. So the dynamics are somehow the result of the model itself. Therefore, as already mentioned, it depends on the purpose of the model, which one is the better one for your problem or for something that you want to explain or analyze.